Chapter 5. Aerodynamics of Flight. Forces acting on the aircraft. Thrust, drag, lift, and weight are forces that act upon all aircraft in flight. Understanding how these forces work and knowing how to control them with the use of power and flight controls are essential to flight. This chapter discusses the aerodynamics of flight, how design, weight, load factors, and gravity affect an aircraft during flight maneuvers. The four forces acting on an aircraft in straight and level, unaccelerated flight are thrust, drag, lift, and weight. They are defined as follows. 1. Thrust, the forward force produced by the powerplant/propeller or rotor. It opposes or overcomes the force of drag. As a general rule, it acts parallel to the longitudinal axis. However, this is not always the case, as explained later. 2. Drag, a rearward, retarding force caused by disruption of airflow by the wing, rotor, fuselage, and other protruding objects. As a general rule, drag opposes thrust and acts rearward parallel to the relative wind. 3. Lift is a force that is produced by the dynamic effect of the air acting on the airfoil, and acts perpendicular to the flight path through the center of lift, CL, and perpendicular to the lateral axis. In level flight, lift opposes the downward force of weight. End of page 5-1. For weight, the combined load of the aircraft itself, the crew, the fuel, and the cargo or baggage. Weight is a force that pulls the aircraft downward because of the force of gravity. It opposes lift and acts vertically downward through the aircraft's center of gravity, CG. In steady flight, the sum of these opposing forces is always zero. There can be no unbalanced forces in steady, straight flight based upon Newton's third law, which states that for every action or force there is an equal, but opposite, reaction or force. This is true whether flying level or when climbing or descending. It does not mean the four forces are equal. It means the opposing forces are equal to, and thereby cancel, the effects of each other. In Figure 5.1, the force vectors of thrust, drag, lift, and weight appear to be equal in value. The usual explanation states, without stipulating that thrust and drag do not equal weight and lift, that thrust equals drag and lift equals weight. Although true, this statement can be misleading. It should be understood that in straight, level, unaccelerated flight, it is true that the opposing lift/weight forces are equal. They are also greater than the opposing forces of thrust/drag that are equal only to each other. Therefore, in steady flight, 1. The sum of all upward components of forces, not just lift, equals the sum of all downward components of forces, not just weight. 2. The sum of all forward components of forces, not just thrust, equals the sum of all backward components of forces, not just drag. This refinement of the old thrust equals drag, lift equals weight formula explains that a portion of thrust is directed weight lift upward in climbs and slow flight and acts as if it were lift, while a portion of weight is directed backward opposite to the direction of flight and acts as if it were drag. In slow flight, thrust has an upward component. But because the aircraft is in level flight, weight does not contribute to drag. Figure 5.2. In glides, a portion of the weight vector is directed along the forward flight path and, therefore, acts as thrust. In other words, anytime the flight path of the aircraft is not horizontal, lift, weight, thrust, and drag vectors must each be broken down into two components. Another important concept to understand is angle of attack, AOA. Since the early days of flight, AOA is fundamental to understanding many aspects of airplane performance, stability, and control. The AOA is defined as the acute angle between the chord line of the airfoil and the direction of the relative wind. Discussions of the preceding concepts are frequently omitted in aeronautical texts/handbooks/manuals. The reason is not that they are inconsequential, but because the main ideas with respect to the aerodynamic forces acting upon an aircraft in flight can be presented in their most essential elements without being involved in the technicalities of the aerodynamicist. In point of fact, considering only level flight and normal climbs and glides in a steady state, it is still true that lift provided by the wing or rotor is the primary upward force, and weight is the primary downward force. By using the aerodynamic forces of thrust, drag, lift, and weight, pilots can fly a controlled, safe flight. A more detailed discussion of these forces follows. Thrust. For an aircraft to start moving, thrust must be exerted and be greater than drag. The aircraft continues to move and gain speed until thrust and drag are equal. In order to maintain a constant airspeed, thrust and drag must remain equal, just as lift and weight must be equal to maintain a constant altitude. End of page 5-2. If in level flight, the engine power is reduced, the thrust is lessened, and the aircraft slows down. As long as the thrust is less than the drag, the aircraft continues to decelerate. To a point, as the aircraft slows down, the drag force will also decrease. The aircraft will continue to slow down until thrust again equals drag, at which point the airspeed will stabilize. Likewise, if the engine power is increased, thrust becomes greater than drag and the airspeed increases. As long as the thrust continues to be greater than the drag, the aircraft continues to accelerate. When drag equals thrust, the aircraft flies at a constant airspeed. Straight and level flight may be sustained at a wide range of speeds. The pilot coordinates AOA and thrust in all speed regimes if the aircraft is to be held in level flight. An important fact related to the principle of lift, for a given airfoil shape, is that lift varies with the AOA and airspeed. Therefore, a large AOA at low airspeeds produces an equal amount of lift at high airspeeds with a low AOA. The speed regimes of flight can be grouped in three categories: low-speed flight, cruising flight, and high-speed flight. When the airspeed is low, the AOA must be relatively high if the balance between lift and weight is to be maintained. Figure 5.3. If thrust decreases and airspeed decreases, lift will become less than weight and the aircraft will start to descend. To maintain level flight, the pilot can increase the AOA an amount that generates a lift force again equal to the weight of the aircraft. While the aircraft will be flying more slowly, it will still maintain level flight. The AOA is adjusted to maintain lift equal weight. The airspeed will naturally adjust until drag equals thrust and then maintain that airspeed, assumes the pilot is not trying to hold an exact speed. Straight and level flight in the slow speed regime provides some interesting conditions relative to the equilibrium of forces. With the aircraft in a nose-high attitude, there is a vertical component of thrust that helps support it. For one thing, wing loading tends to be less than would be expected. In level flight, when thrust is increased, the aircraft speeds up and the lift increases. The aircraft will start to climb unless the AOA is decreased just enough to maintain the relationship between lift and weight. The timing of this decrease in AOA needs to be coordinated with the increase in thrust and airspeed. Otherwise, if the AOA is decreased too fast, the aircraft will descend, and if the AOA is decreased too slowly, the aircraft will climb. As the airspeed varies due to thrust, the AOA must also vary to maintain level flight. At very high speeds in level flight, it is even possible to have a slightly negative AOA. As thrust is reduced and airspeed decreases, the AOA must increase in order to maintain altitude. If speed decreases enough, the required AOA will increase to the critical AOA. Any further increase in the AOA will result in the wing stalling. Therefore, extra vigilance is required at reduced thrust settings and low speeds so as not to exceed the critical angle of attack. If the airplane is equipped with an AOA indicator, it should be referenced to help monitor the proximity to the critical AOA. Some aircraft have the ability to change the direction of the thrust rather than changing the AOA. This is accomplished either by pivoting the engines or by vectoring the exhaust gases. Figure 5.4. Lift. The pilot can control the lift. Anytime the control yoke or stick is moved fore or aft, the AOA is changed. As the AOA increases, lift increases, all other factors being equal. When the aircraft reaches the maximum AOA, lift begins to diminish rapidly. This is the stalling AOA, known as CLmax critical AOA. Examine Figure 5.5, noting how the CL increases until the critical AOA is reached, then decreases rapidly with any further increase in the AOA. Before proceeding further with the topic of lift and how it can be controlled, velocity must be discussed. The shape of the wing or rotor cannot be effective unless it continually keeps attacking new air. If an aircraft is to keep flying, the lift-producing airfoil must keep moving. In a helicopter or gyroplane, this is accomplished by the rotation of the rotor blades. For other types of aircraft, such as airplanes, weight shift control, or gliders, air must be moving across the lifting surface. End of page 5-3. This is accomplished by the forward speed of the aircraft. Lift is proportional to the square of the aircraft's velocity. For example, an airplane traveling at 200 knots has 4 times the lift as the same airplane traveling at 100 knots, if the AOA and other factors remain constant. The above lift equation exemplifies this mathematically and supports the doubling of the airspeed will result in 4 times the lift. As a result, one can see that velocity is an important component to the production of lift, which itself can be affected through varying AOA. When examining the equation, lift, L, is determined through the relationship of the air density, ρ, the airfoil velocity, v, the surface area of the wing, S, and the coefficient of lift, CL, for a given airfoil. Taking the equation further, one can see an aircraft could not continue to travel in level flight at a constant altitude and maintain the same AOA if the velocity is increased. The lift would increase and the aircraft would climb as a result of the increased lift force or speed up. Therefore, to keep the aircraft straight and level, not accelerating upward, and in a state of equilibrium, as velocity is increased, lift must be kept constant. This is normally accomplished by reducing the AOA by lowering the nose. Conversely, as the aircraft is slowed, the decreasing velocity requires increasing the AOA to maintain lift sufficient to maintain flight. There is, of course, a limit to how far the AOA can be increased if a stall is to be avoided. All other factors being constant, for every AOA there is a corresponding airspeed required to maintain altitude in steady, unaccelerated flight, true only if maintaining level flight. Since an airfoil always stalls at the same AOA, if increasing weight, lift must also be increased. The only method of increasing lift is by increasing velocity if the AOA is held constant just short of the critical, or stalling, AOA, assuming no flaps or other high lift devices. End of page 5-4. Lift and drag also vary directly with the density of the air. Density is affected by several factors: pressure, temperature, and humidity. At an altitude of 18,000 feet, the density of the air has 1/2 the density of air at sea level. In order to maintain its lift at a higher altitude, an aircraft must fly at a greater true airspeed for any given AOA. Warm air is less dense than cool air, and moist air is less dense than dry air. Thus, on a hot humid day, an aircraft must be flown at a greater true airspeed for any given AOA than on a cool, dry day. If the density factor is decreased and the total lift must equal the total weight to remain in flight, it follows that one of the other factors must be increased. The factor usually increased is the airspeed or the AOA because these are controlled directly by the pilot. Lift varies directly with the wing area, provided there is no change in the wing's planform. If the wings have the same proportion in airfoil sections, a wing with a planform area of 200 square feet lifts twice as much at the same AOA as a wing with an area of 100 square feet. Two major aerodynamic factors from the pilot's viewpoint are lift and airspeed because they can be controlled readily and accurately. Of course, the pilot can also control density by adjusting the altitude and can control wing area if the aircraft happens to have flaps of the type that enlarge wing area. However, for most situations, the pilot controls lift and airspeed to maneuver an aircraft. For instance, in straight and level flight, cruising along at a constant altitude is maintained by adjusting lift to match the aircraft's velocity or cruise airspeed, while maintaining a state of equilibrium in which lift equals weight. In an approach to landing, when the pilot wishes to land as slowly as practical, it is necessary to increase AOA near maximum to maintain lift equal to the weight of the aircraft. Lift/drag ratio. The lift-to-drag ratio, L/D, is the amount of lift generated by a wing or airfoil compared to its drag. A ratio of L/D indicates airfoil efficiency. Aircraft with higher L/D ratios are more efficient than those with lower L/D ratios. In unaccelerated flight with the lift and drag data steady, the proportions of the coefficient of lift, CL, and coefficient of drag, CD, can be calculated for specific AOA. Figure 5.5 The coefficient of lift is dimensionless and relates the lift generated by a lifting body, the dynamic pressure of the fluid flow around the body, and a reference area associated with the body. The coefficient of drag is also dimensionless and is used to quantify the drag of an object in a fluid environment, such as air, and is always associated with a particular surface area. The L/D ratio is determined by dividing the CL by the CD, which is the same as dividing the lift equation by the drag equation, as all of the variables, aside from the coefficients, cancel out. The lift and drag equations are as follows. L equals lift in pounds, D equals drag, CL equals coefficient of lift, rho equals density, expressed in slugs per cubic feet, V equals velocity, in feet per second, Q equals dynamic pressure per square foot, Q equals 1/2 rho V2, S equals the area of the lifting body, in square feet, and CD equals ratio of drag pressure to dynamic pressure. Typically at low AOA, the coefficient of drag is low and small changes in AOA create only slight changes in the coefficient of drag. At high AOA, small changes in the AOA cause significant changes in drag. The shape of an airfoil, as well as changes in the AOA, affects the production of lift. Notice in Figure 5.5 that the coefficient of lift curve, red, reaches its maximum for this particular wing section at 20 degrees AOA and then rapidly decreases. 20 degrees AOA is therefore the critical angle of attack. The coefficient of drag curve, orange, increases very rapidly from 14 degrees AOA and completely overcomes the lift curve at 21 degrees AOA. The lift/drag ratio, green, reaches its maximum at 6 degrees AOA, meaning that at this angle, the most lift is obtained for the least amount of drag. Note that the maximum lift/drag ratio, L/D max, occurs at one specific CL and AOA. If the aircraft is operated in steady flight at L/D max, the total drag is at a minimum. Any AOA lower or higher than that for L/D max reduces the L/D and consequently increases the total drag for a given aircraft's lift. End of page 5-5. Figure 5.6 depicts the L/D max by the lowest portion of the blue line labeled total drag. The configuration of an aircraft has a great effect on the L/D. Drag. Drag is the force that resists movement of an aircraft through the air. There are two basic types, parasite drag and induced drag. The first is called parasite because it in no way functions to aid flight, while the second, induced drag, is a result of an airfoil developing lift. Parasite drag. Parasite drag is comprised of all the forces that work to slow an aircraft's movement. As the term parasite implies, it is the drag that is not associated with the production of lift. This includes the displacement of the air by the aircraft, turbulence generated in the airstream, or a hindrance of air moving over the surface of the aircraft in airfoil. There are three types of parasite drag: form drag, interference drag, and skin friction. Form drag. Form drag is the portion of parasite drag generated by the aircraft due to its shape and airflow around it. Examples include the engine cowlings, antennas, and the aerodynamic shape of other components. When the air has to separate to move around a moving aircraft and its components, it eventually rejoins after passing the body. How quickly and smoothly it rejoins is representative of the resistance that it creates, which requires additional force to overcome. Figure 5.7. Notice how the flat plate in Figure 5.7 causes the air to swirl around the edges until it eventually rejoins downstream. Form drag is the easiest to reduce when designing an aircraft. The solution is to streamline as many of the parts as possible. Interference drag. Interference drag comes from the intersection of airstreams that creates eddy currents, turbulence, or restricts smooth airflow. For example, the intersection of the wing and the fuselage at the wing root has significant interference drag. Air flowing around the fuselage collides with air flowing over the wing, merging into a current of air different from the two original currents. The most interference drag is observed when two surfaces meet at perpendicular angles. Fairings are used to reduce this tendency. If a jet fighter carries two identical wing tanks, the overall drag is greater than the sum of the individual tanks because both of these create and generate interference drag. Fairings and distance between lifting surfaces and external components, such as radar antennas hung from wings, reduce interference drag. Figure 5.8. Skin friction drag. Skin friction drag is the aerodynamic resistance due to the contact of moving air with the surface of an aircraft. Every surface, no matter how apparently smooth, has a rough, ragged surface when viewed under a microscope. The air molecules, which come in direct contact with the surface of the wing, are virtually motionless. Each layer of molecules above the surface moves slightly faster until the molecules are moving at the velocity of the air moving around the aircraft. This speed is called the freestream velocity. The area between the wing and the freestream velocity level is about as wide as a playing card and is called the boundary layer. At the top of the boundary layer, the molecules increase velocity and move at the same speed as the molecules outside the boundary layer. The actual speed at which the molecules move depends upon the shape of the wing, the viscosity, stickiness of the air through which the wing or airfoil is moving, and its compressibility, how much it can be compacted. End of page 5 to 6. The airflow outside of the boundary layer reacts to the shape of the edge of the boundary layer just as it would to the physical surface of an object. The boundary layer gives any object an effective shape that is usually slightly different from the physical shape. The boundary layer may also separate from the body, thus creating an effective shape much different from the physical shape of the object. This change in the physical shape of the boundary layer causes a dramatic decrease in lift and an increase in drag. When this happens, the airfoil has stalled. In order to reduce the effect of skin friction drag, aircraft designers utilize flush mount rivets and remove any irregularities that may protrude above the wing surface. In addition, a smooth and glossy finish aids in transition of air across the surface of the wing. Since dirt on an aircraft disrupts the free flow of air and increases drag, keep the surfaces of an aircraft clean and waxed. Induced drag. The second basic type of drag is induced drag. It is an established physical fact that no system that does work in the mechanical sense can be 100% efficient. This means that whatever the nature of the system, the required work is obtained at the expense of certain additional work that is dissipated or lost in the system. The more efficient the system, the smaller this loss. In level flight, the aerodynamic properties of a wing or rotor produce a required lift, but this can be obtained only at the expense of a certain penalty. The name given to this penalty is induced drag. Induced drag is inherent whenever an airfoil is producing lift and, in fact, this type of drag is inseparable from the production of lift. Consequently, it is always present if lift is produced. An airfoil, wing or rotor blade, produces the lift force by making use of the energy of the free airstream. Whenever an airfoil is producing lift, the pressure on the lower surface of it is greater than that on the upper surface, Bernoulli's principle. As a result, the air tends to flow from the high pressure area below the tip upward to the low pressure area on the upper surface. In the vicinity of the tips, there is a tendency for these pressures to equalize, resulting in a lateral flow outward from the underside to the upper surface. This lateral flow imparts a rotational velocity to the air at the tips, creating vortices that trail behind the airfoil. When the aircraft is viewed from the tail, these vortices circulate counterclockwise about the right tip and clockwise about the left tip. Figure 5.9. As the air and vortices roll off the back of your wing, they angle down, which is known as downwash. Figure 5.10 shows the difference in downwash at altitude versus near the ground. Bearing in mind the direction of rotation of these vortices, it can be seen that they induce an upward flow of air beyond the tip and a downwash flow behind the wing's trailing edge. This induced downwash has nothing in common with the downwash that is necessary to produce lift. It is, in fact, the source of induced drag. Downwash points the relative wind downward, so the more downwash you have, the more your relative wind points downward. That's important for one very good reason: lift is always perpendicular to the relative wind. In Figure 5.11, you can see that when you have less downwash, your lift vector is more vertical, opposing gravity. And when you have more downwash, your lift vector points back more, causing induced drag. On top of that, it takes energy for your wings to create downwash and vortices, and that energy creates drag. End of page 5 to 7. The greater the size and strength of the vortices and consequent downwash component on the net airflow over the airfoil, the greater the induced drag effect becomes. This downwash over the top of the airfoil at the tip has the same effect as bending the lift vector rearward, therefore, the lift is slightly aft of perpendicular to the relative wind, creating a rearward lift component. This is induced drag. In order to create a greater negative pressure on the top of an airfoil, the airfoil can be inclined to a higher AOA. If the AOA of a symmetrical airfoil were 0, there would be no pressure differential, and consequently, no downwash component and no induced drag. In any case, as AOA increases, induced drag increases proportionally. To state this another way, the lower the airspeed, the greater the AOA required to produce lift equal to the aircraft's weight and, therefore, the greater induced drag. The amount of induced drag varies inversely with the square of the airspeed. Conversely, parasite drag increases as the square of the airspeed. Thus, in steady state, as airspeed decreases to near the stalling speed, the total drag becomes greater, due mainly to the sharp rise in induced drag. Similarly, as the aircraft reaches its never-exceed speed, VNE, the total drag increases rapidly due to the sharp increase of parasite drag. As seen in Figure 5.6. At some given airspeed, total drag is at its minimum amount. In figuring the maximum range of aircraft, the thrust required to overcome drag is at a minimum if drag is at a minimum. The minimum power and maximum endurance occur at a different point. Weight. Gravity is the pulling force that tends to draw all bodies to the center of the Earth. The CG may be considered as a point at which all the weight of the aircraft is concentrated. If the aircraft were supported at its exact CG, it would balance in any attitude. It will be noted that CG is of major importance in an aircraft, for its position has a great bearing upon stability. The allowable location of the CG is determined by the general design of each particular aircraft. The designers determine how far the center of pressure, CP, will travel. It is important to understand that an aircraft's weight is concentrated at the CG and the aerodynamic forces of lift occur at the CP. When the CG is forward of the CP, there is a natural tendency for the aircraft to want to pitch nose down. If the CP is forward of the CG, a nose-up pitching moment is created. Therefore, designers fix the aft limit of the CG forward of the CP for the corresponding flight speed in order to retain flight equilibrium. Weight has a definite relationship to lift. This relationship is simple, but important in understanding the aerodynamics of flying. Lift is the upward force on the wing acting perpendicular to the relative wind and perpendicular to the aircraft's lateral axis. Lift is required to counteract the aircraft's weight. In stabilized level flight, when the lift force is equal to the weight force, the aircraft is in a state of equilibrium and neither accelerates upward or downward. If lift becomes less than weight, the vertical speed will decrease. When lift is greater than weight, the vertical speed will increase. Wingtip vortices. Formation of vortices. The action of the airfoil that gives an aircraft lift also causes induced drag. When an airfoil is flown at a positive AOA, a pressure differential exists between the upper and lower surfaces of the airfoil. The pressure above the wing is less than atmospheric pressure and the pressure below the wing is equal to or greater than atmospheric pressure. Since air always moves from high pressure toward low pressure, and the path of least resistance is toward the airfoil's tips, there is a spanwise movement of air from the bottom of the airfoil outward from the fuselage around the tips. This flow of air results in spillage over the tips, thereby setting up a whirlpool of air called a vortex. Figure 5.12. At the same time, the air on the upper surface has a tendency to flow in toward the fuselage and off the trailing edge. This air current forms a similar vortex at the inboard portion of the trailing edge of the airfoil, but because the fuselage limits the inward flow, the vortex is insignificant. Consequently, the deviation in flow direction is greatest at the outer tips where the unrestricted lateral flow is the strongest. End of page 5-8. As the air curls upward around the tip, it combines with the downwash to form a fast-spinning trailing vortex. These vortices increase drag because of energy spent in producing the turbulence. Whenever an airfoil is producing lift, induced drag occurs and wingtip vortices are created. Just as lift increases with an increase in AOA, induced drag also increases. This occurs because as the AOA is increased, there is a greater pressure difference between the top and bottom of the airfoil, and a greater lateral flow of air. Consequently, this causes more violent vortices to be set up, resulting in more turbulence and more induced drag. In Figure 5.12, it is easy to see the formation of wingtip vortices. The intensity or strength of the vortices is directly proportional to the weight of the aircraft and inversely proportional to the wingspan and speed of the aircraft. The heavier and slower the aircraft, the greater the AOA and the stronger the wingtip vortices. Thus, an aircraft will create wingtip vortices with maximum strength occurring during the takeoff, climb, and landing phases of flight. These vortices lead to a particularly dangerous hazard to flight: wake turbulence. Avoiding wake turbulence. Wingtip vortices are greatest when the generating aircraft is heavy, clean, and slow. This condition is most commonly encountered during approaches or departures because an aircraft's AOA is at the highest to produce the lift necessary to land or take off. To minimize the chances of flying through an aircraft's wake turbulence: 1. Avoid flying through another aircraft's flight path. 2. Rotate prior to the point at which the preceding aircraft rotated when taking off behind another aircraft. 3. Avoid following another aircraft on a similar flight path at an altitude within 1,000 feet. Figure 5.13. 4. Approach the runway above a preceding aircraft's path when landing behind another aircraft and touch down after the point at which the other aircraft wheels contacted the runway. Figure 5.14. A hovering helicopter generates a downwash from its main rotors similar to the vortices of an airplane. Pilots of small aircraft should avoid a hovering helicopter by at least 3 rotor disc diameters to avoid the effects of this downwash. In forward flight, this energy is transformed into a pair of strong, high-speed trailing vortices similar to wingtip vortices of larger fixed-wing aircraft. Helicopter vortices should be avoided because helicopter forward flight airspeeds are often very slow and can generate exceptionally strong wake turbulence. Wind is an important factor in avoiding wake turbulence because wingtip vortices drift with the wind at the speed of the wind. For example, a wind speed of 10 knots causes the vortices to drift at about 1,000 feet in a minute in the wind direction. When following another aircraft, a pilot should consider wind speed and direction when selecting an intended takeoff or landing point. If a pilot is unsure of the other aircraft's takeoff or landing point, approximately 3 minutes provides a margin of safety that allows wake turbulence dissipation. End of page 5-9. Figure 5.14. Avoid turbulence from another aircraft. Figure 5.15. When the vortices of larger aircraft sink close to the ground, within 100 to 200 feet, they tend to move laterally over the ground at a speed of 2 or 3 knots, top. A crosswind will decrease the lateral movement of the upwind vortex and increase the movement of the downwind vortex. Thus, a light wind with a cross-runway component of 1 to 5 knots could result in the upwind vortex remaining in the touchdown zone for a period of time and hasten the drift of the downwind vortex toward another runway, bottom. End of page 5-10, Figure 5.15. For more information on wake turbulence, see Advisory Circular AC 90-23, Aircraft Wake Turbulence. Ground effect. Ever since the beginning of manned flight, pilots realized that just before touchdown it would suddenly feel like the aircraft did not want to go lower, and it would just want to go on and on. This is due to the air that is trapped between the wing and the landing surface, as if there were an air cushion. This phenomenon is called ground effect. When an aircraft in flight comes within several feet of the surface, ground or water, a change occurs in the three-dimensional flow pattern around the aircraft because the vertical component of the airflow around the wing is restricted by the surface. This alters the wing's upwash, downwash, and wingtip vortices. Figure 5.16. Ground effect, then, is due to the interference of the ground, or water, surface with the airflow patterns about the aircraft in flight. While the aerodynamic characteristics of the tail surfaces and the fuselage are altered by ground effect, the principal effects due to proximity of the ground are the changes in the aerodynamic characteristics of the wing. As the wing encounters ground effect and is maintained at a constant AOA, there is consequent reduction in the upwash, downwash, and wingtip vortices. Induced drag is a result of the airfoil's work of sustaining the aircraft, and a wing or rotor lifts the aircraft simply by accelerating a mass of air downward. It is true that reduced pressure on top of an airfoil is essential to lift, but that is only one of the things contributing to the overall effect of pushing an air mass downward. The more downwash there is, the harder the wing pushes the mass of air down. At high angles of attack, the amount of induced drag is high. Since this corresponds to lower airspeeds in actual flight, it can be said that induced drag predominates at low speed. However, the reduction of the wingtip vortices due to ground effect alters the spanwise lift distribution and reduces the induced AOA and induced drag. Therefore, the wing will require a lower AOA in ground effect to produce the same CL. If a constant AOA is maintained, an increase in CL results. Figure 5.17. Ground effect also alters the thrust required versus velocity. Since induced drag predominates at low speeds, the reduction of induced drag due to ground effect will cause a significant reduction of thrust required, parasite plus induced drag, at low speeds. Due to the change in upwash, downwash, and wingtip vortices, there may be a change in position, installation, error of the airspeed system associated with ground effect. In the majority of cases, ground effect causes an increase in the local pressure at the static source and produces a lower indication of airspeed in altitude. Thus, an aircraft may be airborne at an indicated airspeed less than that normally required. In order for ground effect to be of significant magnitude, the wing must be quite close to the ground. One of the direct results of ground effect is the variation of induced drag with wing height above the ground at a constant CL. When the wing is at a height equal to its span, the reduction in induced drag is only 1.4%. However, when the wing is at a height equal to 1/4 its span, the reduction in induced drag is 23.5%, and, when the wing is at a height equal to 1/10 its span, the reduction in induced drag is 47.6%. Thus, a large reduction in induced drag takes place only when the wing is very close to the ground. Because of this variation, ground effect is most usually recognized during the liftoff or takeoff or just prior to touchdown when landing. End of page 5 to 11. During the takeoff phase of flight, ground effect produces some important relationships. An aircraft leaving ground effect after takeoff encounters just the reverse of an aircraft entering ground effect during landing. The aircraft leaving ground effect will 1. Require an increase in AOA to maintain the same CL. 2. Experience an increase in induced drag and thrust required. 3. Experience a decrease in stability and a nose-up change in moment. 4. Experience a reduction in static source pressure and increase in indicated airspeed. Ground effect must be considered during takeoffs and landings. For example, if a pilot fails to understand the relationship between the aircraft and ground effect during takeoff, a hazardous situation is possible because the recommended takeoff speed may not be achieved. Due to the reduced drag and ground effect, the aircraft may seem capable of takeoff well below the recommended speed. As the aircraft rises out of ground effect with a deficiency of speed, the greater induced drag may result in marginal initial climb performance. In extreme conditions, such as high gross weight, high density altitude, and high temperature, a deficiency of airspeed during takeoff may permit the aircraft to become airborne but be incapable of sustaining flight out of ground effect. In this case, the aircraft may become airborne initially with a deficiency of speed and then settle back to the runway. A pilot should not attempt to force an aircraft to become airborne with a deficiency of speed. The manufacturer's recommended takeoff speed is necessary to provide adequate initial climb performance. It is also important that a definite climb be established before a pilot retracts the landing gear or flaps. Never retract the landing gear or flaps prior to establishing a positive rate of climb and only after achieving a safe altitude. If, during the landing phase of flight, the aircraft is brought into ground effect with a constant AOA, the aircraft experiences an increase in CL and a reduction in the thrust required, and a floating effect may occur. Because of the reduced drag and lack of power-off deceleration in ground effect, any excess speed at the point of flare may incur a considerable float distance. As the aircraft nears the point of touchdown, ground effect is most realized at altitudes less than the wingspan. During the final phases of the approach as the aircraft nears the ground, a reduction of power is necessary to offset the increase in lift caused from ground effect, otherwise the aircraft will have a tendency to climb above the desired glide path, GP. Axes of an aircraft. The axes of an aircraft are three imaginary lines that pass through an aircraft's CG. The axes can be considered as imaginary axles around which the aircraft turns. The three axes pass through the CG at 90 degrees angles to each other. The axis passes through the CG in parallel to a line from nose to tail is the longitudinal axis, the axis that passes parallel to a line from wingtip to wingtip is the lateral axis, and the axis that passes through the CG at right angles to the other two axes is the vertical axis. Whenever an aircraft changes its flight attitude or position in flight, it rotates about one or more of the three axes. Figure 5.18. The aircraft's motion about its longitudinal axis resembles the roll of a ship from side to side. In fact, the names used to describe the motion about an aircraft's three axes were originally nautical terms. They have been adapted to aeronautical terminology due to the similarity of motion of aircraft and seagoing ships. The motion about the aircraft's longitudinal axis is roll, the motion about its lateral axis is pitch, and the motion about its vertical axis is yaw. Yaw is the left and right movement of the aircraft's nose. End of page 5 to 12. The three motions of the conventional airplane, roll, pitch, and yaw, are controlled by three control surfaces. Roll is controlled by the ailerons, pitch is controlled by the elevators, yaw is controlled by the rudder. The use of these controls is explained in Chapter 6, Flight Controls. Other types of aircraft may utilize different methods of controlling the movements about the various axes. For example, weight-shift control aircraft control two axes, roll and pitch, using an A-frame suspended from the flexible wing attached to a three-wheeled carriage. These aircraft are controlled by moving a horizontal bar, called a control bar, in roughly the same way hang glider pilots fly. Figure 5.19, they are termed weight-shift control aircraft because the pilot controls the aircraft by shifting the CG. For more information on weight-shift control aircraft, see the Federal Aviation Administration, FAA. Weight Shift Control Flying Handbook, FAA-H-8083-25. In the case of powered parachutes, aircraft control is accomplished by altering the airfoil via steering lines. A powered parachute wing is a parachute that has a cambered upper surface and a flatter under surface. The two surfaces are separated by ribs that act as cells, which open to the airflow at the leading edge and have internal ports to allow lateral airflow. The principle at work holds that the cell pressure is greater than the outside pressure, thereby forming a wing that maintains its airfoil shape in flight. The pilot and passengers sit in tandem in front of the engine, which is located at the rear of a vehicle. The airframe is attached to the parachute via two attachment points and lines. Control is accomplished by both power and the changing of the airfoil via the control lines. Figure 5.20. Moment and moment arm. A study of physics shows that a body that is free to rotate will always turn about its CG. In aerodynamic terms, the mathematical measure of an aircraft's tendency to rotate about its CG is called a moment. A moment is said to be equal to the product of the force applied and the distance at which the force is applied. A moment arm is the distance from a datum, reference point or line, to the applied force. For aircraft weight and balance computations, moments are expressed in terms of the distance of the arm times the aircraft's weight, or simply, inch-pounds. Aircraft designers locate the fore and aft position of the aircraft's CG as nearly as possible to the 20% point of the mean aerodynamic chord, Mach. If the thrust line is designed to pass horizontally through the CG, it will not cause the aircraft to pitch when power is changed, and there will be no difference in moment due to thrust for a power-on or power-off condition of flight. Although designers have some control over the location of the drag forces, they are not always able to make the resultant drag forces pass through the CG of the aircraft. However, the one item over which they have the greatest control is the size and location of the tail. The objective is to make the moments, due to thrust, drag, and lift, as small as possible and, by proper location of the tail, to provide the means of balancing an aircraft longitudinally for any condition of flight. The pilot has no direct control over the location of forces acting on the aircraft in flight, except for controlling the center of lift by changing the AOA. The pilot can control the magnitude of the forces. Such a change, however, immediately involves changes in other forces. Therefore, the pilot cannot independently change the location of one force without changing the effect of others. For example, a change in airspeed involves a change in lift, as well as a change in drag and a change in the up or down force on the tail. End of page 5 to 13. As forces such as turbulence and gusts act to displace the aircraft, the pilot reacts by providing opposing control forces to counteract this displacement. Some aircraft are subject to changes in the location of the CG with variations of load. Trimming devices, such as elevator trim tabs and adjustable horizontal stabilizers, are used to counteract the moments set up by fuel burn-off and loading or offloading of passengers or cargo. Aircraft design characteristics. Each aircraft handles somewhat differently because each resists or responds to control pressures in its own way. For example, a training aircraft is quick to respond to control applications, while a transport aircraft feels heavy on the controls and responds to control pressures more slowly. These features can be designed into an aircraft to facilitate the particular purpose of the aircraft by considering certain stability and maneuvering requirements. The following discussion summarizes the more important aspects of an aircraft's stability, maneuverability, and controllability qualities, how they are analyzed, and their relationship to various flight conditions. Stability. Stability is the inherent quality of an aircraft to correct for conditions that may disturb its equilibrium and to return to or to continue on the original flight path. It is primarily an aircraft design characteristic. The flight paths and attitudes an aircraft flies are limited by the aerodynamic characteristics of the aircraft, its propulsion system, and its structural strength. These limitations indicate the maximum performance and maneuverability of the aircraft. If the aircraft is to provide maximum utility, it must be safely controllable to the full extent of these limits without exceeding the pilot's strength or requiring exceptional flying ability. If an aircraft is to fly straight and steady along any arbitrary flight path, the forces acting on it must be in static equilibrium. The reaction of any body when its equilibrium is disturbed is referred to as stability. The two types of stability are static and dynamic. Static stability. Static stability refers to the initial tendency, or direction of movement, back to equilibrium. In aviation, it refers to the aircraft's initial response when disturbed from a given pitch, yaw, or bank. 1. Positive static stability, the initial tendency of the aircraft to return to the original state of equilibrium after being disturbed. Figure 5.21. 2. Neutral static stability, the initial tendency of the aircraft to remain in a new condition after its equilibrium has been disturbed. Figure 5.21. 3. Negative static stability, the initial tendency of the aircraft to continue away from the original state of equilibrium after being disturbed. Figure 5.21. Dynamic stability. Static stability has been defined as the initial tendency to return to equilibrium that the aircraft displays after being disturbed from its trimmed condition. Occasionally, the initial tendency is different or opposite from the overall tendency, so a distinction must be made between the two. Dynamic stability refers to the aircraft response over time when disturbed from a given pitch, yaw, or bank. This type of stability also has three subtypes, figure 5.22. End of page 5 to 14. 1. Positive dynamic stability. Over time, the motion of the displaced object decreases in amplitude and, because it is positive, the object displaced returns toward the equilibrium state. 2. Neutral dynamic stability. Once displaced, the displaced object neither decreases nor increases in amplitude. A worn automobile shock absorber exhibits this tendency. 3. Negative dynamic stability. Over time, the motion of the displaced object increases and becomes more divergent. Stability in an aircraft affects two areas significantly. 1. Maneuverability, the quality of an aircraft that permits it to be maneuvered easily and to withstand the stresses imposed by maneuvers. It is governed by the aircraft's weight, inertia, size and location of flight controls, structural strength, and power plant. It too is an aircraft design characteristic. 2. Controllability, the capability of an aircraft to respond to the pilot's control, especially with regard to flight path and attitude. It is the quality of the aircraft's response to the pilot's control application when maneuvering the aircraft, regardless of its stability characteristics. Longitudinal stability, pitching. In designing an aircraft, a great deal of effort is spent in developing the desired degree of stability around all three axes. But longitudinal stability about the lateral axis is considered to be the most affected by certain variables in various flight conditions. Longitudinal stability is the quality that makes an aircraft stable about its lateral axis. It involves the pitching motion as the aircraft's nose moves up and down in flight. A longitudinally unstable aircraft has a tendency to dive or climb progressively into a very steep dive or climb, or even a stall. Thus, an aircraft with longitudinal instability becomes difficult and sometimes dangerous to fly. Static longitudinal stability, or instability in an aircraft, is dependent upon three factors. 1. Location of the wing with respect to the CG. 2. Location of the horizontal tail surfaces with respect to the CG. 3. Area or size of the tail surfaces. In analyzing stability, it should be recalled that a body free to rotate always turns about its CG. To obtain static longitudinal stability, the relation of the wing and tail moments must be such that, if the moments are initially balanced and the aircraft is suddenly nose up, the wing moments and tail moments change so that the sum of their forces provides an unbalanced but restoring moment which, in turn, brings the nose down again. Similarly, if the aircraft is nose down, the resulting change in moments brings the nose back up. The center of lift, CL, in most asymmetrical airfoils has a tendency to change its fore and aft positions with a change in the AOA. The CL tends to move forward with an increase in AOA and to move aft with a decrease in AOA. This means that when the AOA of an airfoil is increased, the CL, by moving forward, tends to lift the leading edge of the wing still more. End of page 5 to 15. This tendency gives the wing an inherent quality of instability. Note, CL is also known as the center of pressure, CP. Figure 5.23 shows an aircraft in straight and level flight. The line CG-CLT represents the aircraft's longitudinal axis from the CG to a point T on the horizontal stabilizer. Most aircraft are designed so that the wing's CL is to the rear of the CG. This makes the aircraft nose heavy and requires that there be a slight downward force on the horizontal stabilizer in order to balance the aircraft and keep the nose from continually pitching downward. Compensation for this nose heaviness is provided by setting the horizontal stabilizer at a slight negative AOA. The downward force thus produced holds the tail down, counterbalancing the heavy nose. It is as if the line CG-CLT were a lever with an upward force at CL and two downward forces balancing each other, one a strong force at the CG point and the other, a much lesser force, at point T, downward air pressure on the stabilizer. To better visualize this physics principle, if an iron bar were suspended at point CL, with a heavy weight hanging on it at the CG, it would take downward pressure at point T to keep the lever in balance. Even though the horizontal stabilizer may be level when the aircraft is in level flight, there is a downwash of air from the wings. This downwash strikes the top of the stabilizer and produces a downward pressure, which at a certain speed is just enough to balance the lever. The faster the aircraft is flying, the greater this downwash and the greater the downward force on the horizontal stabilizer, except T-tails. Figure 5.24. In aircraft with fixed position horizontal stabilizers, the aircraft manufacturer sets the stabilizer at an angle that provides the best stability, or balance, during flight at the design cruising speed and power setting. If the aircraft's speed decreases, the speed of the airflow over the wing is decreased. As a result of this decreased flow of air over the wing, the downwash is reduced, causing a lesser downward force on the horizontal stabilizer. In turn, the characteristic nose heaviness is accentuated, causing the aircraft's nose to pitch down more. Figure 5.25. This places the aircraft in a nose-low attitude, lessening the wing's AOA and drag and allowing the airspeed to increase. As the aircraft continues in the nose-low attitude and its speed increases, the downward force on the horizontal stabilizer is once again increased. Consequently, the tail is again pushed downward and the nose rises into a climbing attitude. End of page 5 to 16. As this climb continues, the airspeed again decreases, causing the downward force on the tail to decrease until the nose lowers once more. Because the aircraft is dynamically stable, the nose does not lower as far this time as it did before. The aircraft acquires enough speed in this more gradual dive to start it into another climb, but the climb is not as steep as the preceding one. After several of these diminishing oscillations, in which the nose alternately rises and lowers, the aircraft finally settles down to a speed at which the downward force on the tail exactly counteracts the tendency of the aircraft to dive. When this condition is attained, the aircraft is once again in balanced flight and continues in stabilized flight as long as this attitude and airspeed are not changed. A similar effect is noted upon closing the throttle. The downwash of the wings is reduced and the force at T in figure 5.23 is not enough to hold the horizontal stabilizer down. It seems as if the force at T on the lever were allowing the force of gravity to pull the nose down. This is a desirable characteristic because the aircraft is inherently trying to regain airspeed and re-establish the proper balance. Power or thrust can also have a destabilizing effect in that an increase of power may tend to make the nose rise. The aircraft designer can offset this by establishing a high thrust line wherein the line of thrust passes above the CG. Figures 5.26 and 5-27. In this case, as power or thrust is increased, a moment is produced to counteract the down load on the tail. On the other hand, a very low thrust line would tend to add to the nose-up effect of the horizontal tail surface. Conclusion: with CG forward of the CL and with an aerodynamic tail-down force, the aircraft usually tries to return to a safe flying attitude. The following is a simple demonstration of longitudinal stability. Trim the aircraft 4 hands-off control in level flight. Then, momentarily give the controls a slight push to nose the aircraft down. If, within a brief period, the nose rises towards the original position, the aircraft is statically stable. Ordinarily, the nose passes the original position, that of level flight, and a series of slow pitching oscillations follows. If the oscillations gradually cease, the aircraft has positive stability. If they continue unevenly, the aircraft has neutral stability. If they increase, the aircraft is unstable. Lateral stability, rolling. Stability about the aircraft's longitudinal axis, which extends from the nose of the aircraft to its tail, is called lateral stability. Positive lateral stability helps to stabilize the lateral or rolling effect when one wing gets lower than the wing on the opposite side of the aircraft. There are 4 main design factors that make an aircraft laterally stable: dihedral, sweepback, keel effect, and weight distribution. End of page 5 to 17. Dihedral. Some aircraft are designed so that the outer tips of the wings are higher than the wing roots. The upward angle thus formed by the wings is called dihedral. Figure 5.28. When a gust causes a roll, a sideslip will result. This sideslip causes the relative wind affecting the entire airplane to be from the direction of the slip. When the relative wind comes from the side, the wing slipping into the wind is subject to an increase in AOA and develops an increase in lift. The wing away from the wind is subject to a decrease in angle of attack and develops a decrease in lift. The changes in lift affect a rolling moment tending to raise the windward wing, hence dihedral contributes to a stable roll due to sideslip. Figure 5.29. Sweep back in wing location. Many aspects of an aircraft's configuration can affect its effective dihedral, but 2 major components are wing sweepback and the wing location with respect to the fuselage, such as a low wing or high wing. As a rough estimation, 10 degrees of sweepback on a wing provides about 1 degree of effective dihedral, while a high wing configuration can provide about 5 degrees of effective dihedral over a low wing configuration. A swept-back wing is one in which the leading edge slopes backward. Figure 5.30. When a disturbance causes an aircraft with sweepback to slip or drop a wing, the low wing presents its leading edge at an angle that is more perpendicular to the relative airflow. As a result, the low wing acquires more lift, rises, and the aircraft is restored to its original flight attitude.